Today, in the morning session, we'll have 3 exciting talks. The first one will be given by Nigel Hussey from Rayburn University and Nijmegen Highfield Lab. So Nigel, would you like to share your screen?
Oh, thank you. I hope you can all see that.
Yes, we can see your screen and then
hear me okay? Okay, great. Well, thank you. Thank you very much, Qimao and Junho, Peng Chang and Ming for organizing this workshop through some very trying circumstances. And I guess for many people, this is the first meeting of 2021. So let me also take the opportunity to wish you a less eventful year than we had previously. In view of time, I hope you will forgive me for only giving a rather brief introduction. I understand this is the first talk of the workshop, and I would have liked to give a longer introduction to some of the issues, but I'd like to spend some time also showing new data if that's possible, time permitting. Okay, so first of all, I'd like to thank my collaborators in this work. Work done with James Analytis and his team in Berkeley. Also work done in Tokyo and Kyoto by Taka Shibauchi, Yuji Matsuda, and Shigeru Asahara. Colleagues at Bristol and my group members in Radboud University as well. So in particular, the work of my former student Salvatore Licciardello and my student who's now a doctoral prize fellow, Jake Ayres, and my postdoc Mattia Ciullo. So I think, the idea of there being a pneumatic critical point in materials has been pursued quite ardently over the last decade or so. And it's clear that there are many strongly correlated materials that now exhibit some form of pneumaticity somewhere in their phase diagram. So this breaking of rotational symmetry below some temperature associated often also with a structural transition. And there have been also a lot of theoretical work looking at the possibility that coupling of the quasi-particle excitations to quantum fluctuations of this pneumatic order can give rise to anomalous transport, strange metallic transport, or non-thermal liquid behavior. I'll just give a few examples here. But often, so what we'd like, of course, is to find a material where we can, say, tune across the pneumatic quantum critical point and explore signatures or look for signatures of strange metallicity in that material. And unfortunately, in most cases where pneumatic order is observed, it's also strongly coupled to a second order parameter. And one of probably the most beautiful examples of quantum critical metal, which is the phosphorus doped barium-122 material. Here, the non-thermal liquid behavior is linked to most likely then to the spin density wave QCP, which effectively coincides with the pneumatic one in this material. And I just wanted to show here this beautiful series of experiments from James Analytis' group, showing in the resistivity as you approach the QCP from the overdoped side. Of course, the phosphorus here is isovalently doped, but as you tune, you find that the T-squared resistivity coefficient grows by roughly an order of magnitude, and which seems to be tied also with the growth in the effective mass measured by other techniques such as specific heat or even zero temperature penetration depth. The transverse magnetoresistance shows this remarkable quadrature form, which I've written below here, and also this H over T scaling over more than a decade in temperature. And so this H linear magnetoresistance is really quite unusual, and it now appears to be seen in other correlated systems, and again now seems to be another signature of strange metallic behavior in these quantum critical metals. And most recently, James also showed how the Hall coefficient has two components, and he labels here the strange metal component, which appears to be most strongly peaked at the QCP, around 30% phosphorus doping, And so, which is something actually which drops away with fields and also with temperature and doping. So those are really the three signatures that we kind of focus on in this talk. And our sort of material of choice for looking for such signatures associated perhaps just uniquely with pneumaticity is the iron selenium iron chalcogenide material, which clearly undergoes this trigonal thermic transition and develops pneumaticity, but strong pneumaticity in its Fermi surface, and anisotropic spin fluctuations, and also an anisotropic superconducting order parameter below around 10 Kelvin. And quantum oscillation measurements, for example, have shown evidence for significant mass enhancement in this material. We showed also that the resistivity is T² at low temperatures with a very large coefficient consistent with dominant electron scattering. So what you'd like then is to find tuning parameters that enable you then to suppress this pneumatic transition down to 0 temperature and follow the behavior, the function of the tuning parameter. But what happens, so one of those is of course pressure, but interestingly what's found here is, so here I show effectively the pneumatic susceptibility measured by Raman spectroscopy. And you see here low frequencies as you approach the onset of pneumatic order, you see this marked increase of almost divergence of the pneumatic susceptibility. But then as you increase pressure, that divergence gets sufficient, systematically suppressed. And that suppression, so I think that here the putative pneumatic critical point should be around about 2 gigapascal, so just between the last two panels. And this suppression has been attributed to the quenching of the criticality by the concomitant growth of long-range magnetic order, as you see in this phase diagram here. So before the pneumatic order is suppressed, you get this development of spin density wave phase. And interestingly, the growth of this appears to also tie in with the growth of the superconducting transition temperature with pressure. An alternative way to tune the pneumaticity away is to, of course, use sulfur. And there it's shown indeed that actually the pneumatic susceptibility as measured by elastoresistivity measurements does indeed appear to peak at the point where the TS goes to 0. And so this is interesting because then that suggests that there is indeed signatures of criticality in this system. And at the same time, measurements of the spin lattice relaxation rates suggest that while, of course, as you cross into the pneumatic phase, there's no enhancement of magnetic fluctuations, but they do develop below TS. But as a function of X, although they seem to peak, interestingly, where TC peaks, they do gradually disappear. So at least here where the pneumatic susceptibility is peaking, the spin fluctuations themselves appear to be becoming more suppressed. So that does suggest that you may have here, the criticality itself is related to the pneumaticity and not with accompanying criticality of the spin fluctuations. Okay, so with that in mind, we measured a series of samples, single crystals of this iron selenium sulfur, and what we found was very systematic behavior, where you go from this T² behavior in the pure material to a linear behavior at a doping close to the critical point, and then revert back to T² behavior as you go beyond it. Now here I write these FeSeS 16 as though this is normally 16%. So our samples are, this is the nominal X values. And so there may be in certain samples, these may be slightly different to the actual values. However, the behavior that we observed has been essentially confirmed by Amalia's group in a recent paper, where they showed also for X equals 0, you get this low T² behavior below around 4 or 5 Kelvin. You then at around 17%, nearly where the critical point is, you have T linear resistivity down to the lowest temperatures that were measured. And then around 25%, you see this development of a much flatter T-squared behavior. And indeed, it was also seen quite early on in a paper which unfortunately was never seemed to be published by Arata and co-workers, where again, they've suppressed perhaps in a smaller field than we were using here 35 Tesla, that the resistivity around the pneumatic critical point was indeed vanishing linearly with temperature, and you see it around 21, so just beyond, you get this crossover to more quadratic behavior. I think it's important to suggest here, that this linearity, of course, we haven't extended it down to the lowest temperatures yet, but assuming that it does cross over at some point to T-squared behavior, you can at least get some minimum value for the coefficient of that T-squared behavior. And I just want to compare here the slopes measured both by ourselves and by Amalia's group for the 25% samples, around 25 nanometer centimeters per K squared. So this is the A coefficient of the T squared term. And then the minimum values that we'd expect if you were to cross over here to T squared behavior. And then this shows that there's basically a sort of at least 15 or 20-fold increase in the coefficient over what is rather a narrow doping range as you approach CP. And just compare that with what was seen in barium 122, where again, it was beyond the spin density wave quantum critical point. And here, say even over a wider range of P, variation here is only about the order of 7 or 8. So it's really significant variation in the coefficient. And so we did this systematically, and you can see this crossover here. I show the derivative. So where you have a linear derivative here shows the T squared behavior, crossing over to a T linear or flat derivative at high temperatures, and close to the quantum critical point, you get this linear behavior down to around about 1.5. So certainly in terms of the resistivity, one of those signatures I think is quite clearly there, that you do see non-thermoliquid behavior. You see a regime below which you recover T-squared behavior and a coefficient, particularly from the higher X value side, which appears to show a marked increase on approach to the quantum critical. Okay, so the second aspect was the magnetoresistance and this remarkable quadrature form of the magnetoresistance observed in barium 122 with H over T scaling. So in iron selenium, you see something which doesn't look like it scales, and shows rather complicated behavior, even for a sample close to the QCP. However, when we took the derivative of this magnetoresistance with respect to field, we found something quite surprising. So here I show one for the nominal 10% sample, and you see here at low fields, it's clearly quadratic, so the coefficient is T-linear. But then at high fields, over a very wide doping range, field range, you see that you can effectively fit this to a constant plus a linear term, which means that effectively the magnetoresistance is B plus B squared. And if you subtract off this high field B squared component, what you find is then a magnetoresistance which is linear in field from about 3 or 4 Tesla, and does show the fit here is almost perfect fit to this quadrature form, which was originally seen in the barium 122 material. So somehow the quadrature magnetoresistance was sort of hidden, or is observed in combination with let's say a more conventional pure B squared magnetoresistance. Again, this is something which was seen similarly by Amalia's group, where again, here show derivative around a similar doping level. And you can see again this behavior of this sort of B plus B squared form at high fields and the B squared term at low field. And what was really striking about this is that it was actually there at all doping levels. So here I just again show the full derivatives of some respective curves, all at 15K. So this is all above the superconducting transition temperature. And again, subtracting off this high field B squared term, you see essentially the same form underlying this, which is this quadrature form of the magnetoresistance. And you can isolate that and compare it right across the series, and you see basically at the same temperature, the form looks almost identical. And also you can observe H over T scaling by just comparing the data as a function of temperature. So this quadrature, H over T scaling magnetoresistance, appears to be coming from the strange metal regime. You could associate this with the T linear resistivity. And so this, to our mind, gave us evidence that there were in fact two charged sectors in iron selenium sulfur. And again, if just to make this even clearer, what we looked at a sample from James's group, which had a residual resistivity, which is about 5 times higher than the sample that we'd measured. And here it seems that the magnetoresistance is only showing this quadrature form. So here you see the linear magnetoresistance. You can scale it against H over T. It's as though the orbital magnetoresistance, the conventional component, has been quenched by disorder. But remarkably, this quadrature component appears to survive. So again, we see quite clear evidence then for this second signature of strange metallic behavior, but interestingly observed across the whole, let's say, temperature and X phase diagram that we've studied. And finally, we want to see whether there's any evidence for unusual anomalous Hall coefficients. And reminding you what was seen in the pnictides. So here is low field Hall effect measurements taken by Taka and Yuji's group. And as you see, as you approach towards the QCP, effectively the low temperature RH is getting enhanced progressively. Interestingly, the Hall angle is going as T squared in a regime where the resistivity is predominantly T linear. So we're exhibiting this so-called separation of lifetimes that was famously seen, first of all, in cuprate materials. There's also been seen in pnictides and heavy fermions, among others. So here again, we're seeing an enhancement as you approach the DCP at the low temperature regime of the Hall coefficient. We wanted to look a bit more closely at the field dependence. And so again, we looked at high field Hall coefficient data. This is data which is currently unpublished. It shows quite a complex but systematic evolution with temperature, field, and X. And what we do here is we assume, again, taking our lead from the magnetoresistance, that we have two components to the sigma xy, the normal metallic component and the strange metal component. And noting, again, from James Analytis' group, that the strange component appears to be suppressed in magnetic field, we assume then that the high field term is predominantly given by sigma xy normal metal. And because of the fact that the magnetoresistance for the normal metal component is purely H squared, that suggests very strongly here that we have perfect charge compensation. And so we assume that rho xy for the normal metal component is strictly H linear. And then you can invert this to get the sigma xy for this component. And this is the form then we fit to the as measured sigma xy. Whereas we have taken this assumption that at high fields is where this strange metal component will be suppressed. And so what you see here is the fit at different X values, and in blue is the residual, which we take as this second component. Now this may seem quite somewhat arbitrary, but we've tried to look at 2-carrier, 3-carrier models, compensated or uncompensated, and none of those were able to fit the data satisfactorily at all fields and temperatures, concomitantly with the magnetoresistance. So here ultimately is the rho xy, and again these lines are effectively this form multiplied by H. So it looks like you're getting a similar type of behavior, but again, there are assumptions built into this, so I wouldn't take it too literally at this stage. But if you take the height, or the maximum value here, and look at this as a function of X and T, and we compare it with the strength of the H linear magnetoresistance. So this beta SM was the H linear magnetoresistance, and here is the additional anomalous Hall component. We see quite a reasonable correlation. So what you're seeing here is this is in the T linear regime, marked gray, and then the white is the T squared regime. And you see at low dopings, as you go towards the T-squared regime, these components seem to get smaller. It's also seen on the other side of the dome at 25. And closer to the critical point, these components appear to be getting larger as you go down in temperature. So there's an interesting correlation between the two effects. And finally, we now having got both components, we can look at how they evolve together as a function of temperature. So I'm plotting here RH versus 1 over T. Here is the total as measured value at 16 and 20 values. And you notice that actually the strange metal component appears to just grow as 1 over T, whereas a normal component is almost constant as a function of temperature. And so what you imagine now is that at high temperatures, you're getting this predominantly dominated by the strange metal component. At low temperatures, it's getting shorted out by the normal component. And obviously, we would like to get somewhere in between here to see how these two things evolve. So again, going back to the barium 122 material, it does seem that there are, again, very similar signatures of strange metallicity, strange metallic behavior seen in the iron selenium material. And so, this first sight suggests, well, maybe then we can say that there is indeed quantum critical behavior, which is purely associated with pneumaticity in the material. But this comes hand in hand with some very beautiful quantum oscillation work that was done by Amalia's group, which showed quite clearly that there was no, or very small, mass enhancement measured as given by quantum oscillation measurements across XC. And this is actually quite reminiscent of the situation in the strontium ruthenium material, where strange metallic transport is clearly observed, like an enhancing A coefficient crossing over to T linear behavior, and at the same time, no enhancement in most of the Fermi surface across this critical field in this case. And this has recently been explained as due to effective scattering of hot regions in K-space. You have most of the Fermi surfaces cold, but from a transport perspective, those cold regions are rendered hot by being scattered into these hot regions where in the ruthenate case, there is a high density of states and therefore a higher proliferation of scattering in and out of those regions. Whether the same model can be applied to iron, selenium, sulfur still waits to be seen. Should be added too that these signatures of strange metallic transport are also seen in cuprates, particularly in the overdoped cuprates, where again there's no clear indication of mass enhancement. So that's quite a curious feature of these data. So in the last couple of minutes, I'd just like to show you maybe again looking for further evidence here by looking in the pressure plane. So there was following this very systematic, comprehensive measurements done by Yuji and Taka, where they looked at effectively the transport as a function of X and pressure, and found that as the pneumatic regime is systematically suppressed as you add sulfur, the spin density wave phase basically gets shifted to higher values in the pressure plane, and therefore the thinking is then that also in the pressure plane there may be a region where you're delineating between the pneumatic order or the pneumatic critical point and the spin density wave critical point. Indeed, this is exactly one of the things which Amalia's group did. I'm sure we'll hear further about that in the next talk. So going at around X is 11, they showed indeed that pneumatic criticality appears to be quenched in the system, even though NMR measurements suggest that these two phases, these two critical points are actually isolated. Therefore, the pneumatic phase should have shown evidence of the transport or the mass going critical. That wasn't seen. But actually, quite recent USR data around the similar doping suggests actually that before the pneumatic order is suppressed, there is the emergence of at least slowly fluctuating moments, which may also, again, cause, like they did in iron selenium, in pure iron selenium, cause a suppression of the pneumatic criticality. What we wanted to do was to look at an even higher X values, in fact, at X values beyond the critical points, around 18 and 20% sulfur content, where really, although we don't expect here to be critical, we're clearly seeing we expect to see, let's say, the departure further away from criticality associated with the pneumatic critical point, and maybe an emergence of the critical behavior associated with the magnetism. Okay, so this is what we did. So this is quite a complicated plot, but let me just walk you through it. So what you've got here is the resistivity. These different colors indicate different pressures in kilobar. And you have both 0 field and 35 Tesla data. So you see the 35 Tesla data in both cases always overlaps with the 30. This is with field parallel to the conductive plane. So there's no additional magnetoresistance here. And again, if you take the derivatives of this temperature dependence, so here, this is the ambient pressure data. So you can see this crossover from T squared to T linear behavior in both cases. But then as you go increasing pressure, this T squared component goes down slightly, and this T linear term also goes down. But what's surprising is that there is an emergence of a second T squared term in the derivative. So obviously this will extend all the way down to low temperature, but it's sort of hidden at low temperatures by this higher A coefficient. So we label these three coefficients: A for the low temperature T squared term, B for the T linear term, then A prime for the second term, which emerges and it actually extends over to a much higher temperature. And then we plot that as a function of pressure of the two systems. So you see here the A term is dropping. I should remind you this value of around 75 is intermediate between what we saw for the 25%, which was around 25, and around 16% where it's over 300 or so in nano-ohm centimeters per Kelvin square. The B term is also dropping, and just clearly there's some variation in carrier density here. And so to kind of take that into account, we looked at the value of the resistivity outside of these regimes, around 75K, and you see this dropping away by about 30%, 40% or so. But these changes in the B coefficient are actually much larger, and they seem to be very correlated with the variation in the T-squared component as well. So we assume here that this drop is due to both an increase in carrier density and a decreasing scattering rate as we move further away from the pneumatic QCP. The most striking behavior, though, is in this A prime component. So this is this T-squared term, which extends up to around 30, 40 Kelvin. It starts off extremely small, so it's more than an order of magnitude smaller, but very rapidly it grows. So it grows by roughly an order of magnitude for the 18% sample in the pressure range that we studied. And this growth, again, appears to be correlated with the growth in TC. And as we know from all the measurements that have been done in pressure, under pressure, this growth in TC is believed to be due to an emerging or strengthening of magnetic fluctuations. And so what we can do is ascribe this increasing T-squared coefficient to the emergence of that, or that approach to the magnetic quantum critical point. And that's what's quite remarkable here, is that you actually see the two things separated, suggesting that indeed they're actually coming from different sources. So the scattering due to the magnetism and the scattering which occurs at ambient pressure and would appear to be predominantly due to pneumaticity actually have these different pressure dependencies and different origins. Okay, so that brings me to my conclusions. So iron selenium sulfur basically shows a number of what's called classical signatures of strange metallicity upon suppression of the electronic pneumatic phase by sulfur doping. These are very much similar to those seen in barium iron 122. And so one might also argue, well, does this not then mean that this is also basically scattering of critical fluctuations of a magnetic origin? And if that is the case, then the critical point, at the critical point around 17%, we should also see evidence for magnetic criticality, which, as far as I'm aware, has not been seen yet. The normal state magnetoresistance and the Hall effect show two distinct components, one of which displays these strange metal characteristics. And we believe this is actually one of the first times where we see a coexistence throughout the quantum critical fan of two charged sectors, one the normal metal component and one the strange metal component. And so it's really intriguing to see how these two evolve as a function of the tuning parameter and temperature. The pressure dependence of the resistivity beyond XC does show evidence for two, let's say, T-squared coefficients, which show very strong pressure dependence, the second one of which appears to be correlated with TC and therefore is likely to be of a magnetic origin. And then this, I think, leaves the question open. Chiomel was talking about open questions. I would say here, this clearly suggests, is very suggestive that the origin of strange metal transport is tied to the pneumatic criticality at ambient pressure, but time will tell. And with that, I thank you for your attention.
Thank you very much. Thank you, Nigel, for the beautiful talk. So we're running a bit behind the schedule, but I think we have time for one or two quick questions. So I saw Daniel Komsky.
Yeah, I have one question. In quite a lot of systems, superconducting dome is centered around quantum critical point and TC is maximum above critical point. But here it seems to be not the case. Is it true for at least for pneumatic quantum critical point? TC is actually lower.
Yeah, that's true. In fact,
this color plot.
If anything, that there is a small peak in the TC around 10–11%, which may coincide with the strengthening magnetic fluctuations seen around that doping level. And also you find in the pressure domain.
Can you show actually this last plot when you had this pressure dependence for different X? That's actually
yes.
general plot.
So there I showed TC.
Yeah, no, this color, no, this color plot with many colors.
Yeah.
Well, no, previous one. I have this one, yeah, okay. Here it looks like quantum critical point for pneumatic is a minimum TC. Maybe it is actually maximum TC is close to SDW critical point. Is it possible?
It's possible that, yes, that these peaks here coincide with where spin density wave phase disappears. That is possible. But clearly it looks to, it's certainly with measurements in the pressure domain, that the growth in TC is tied with, certainly with more with the magnetic, the strengthening of magnetic interaction.
But at least pneumatic quantum critical point is not a maximum TC, definitely.
No, it isn't, no.
Okay, very good, thank you.
So I guess here the question here was whether the pneumaticity and the critical fluctuations associated with that could drive strange metal transport rather than be the origin of.
No, I just have in mind these phase diagrams.
Yeah, yeah.
Okay, thank you.
Thank you.
Great. The next one is Qin Miao.
Yeah, Nigel, beautiful talk. So I want to sort of follow up along similar spirit just to see what is universal among these different types of quantum critical points and what is perhaps unique. If you go back to the phosphorus doped baryon 122, clearly there the mass is maximized at the quantum critical point. And that's very typical of heavy fermion quantum critical point and other metallic quantum critical points that we're familiar with. Are you suggesting that at a pneumatic quantum critical point, the mass being maximized at near the quantum critical point is not the case?
Yeah, I mean, I think the question here is, what we're looking at here is signatures in the transport. Mm-hmm. And normally we tie the A coefficient to the effective mass through the say the Kadawaki-Woods scenario, but this is not always the case. So as I mentioned in the strontium ruthenium material, there the A coefficient increases significantly as you approach the critical point with magnetic field, but the effective mass is measured by quantum oscillations do not show similar enhancement, and that's something that's quite unusual. But in the cuprates, for example, as you go from the edge of the superconducting dome, you see the development of this T-linear behavior without any significant variation, again, in, let's say, M stars as determined by specific heat or from quantum oscillation experiments. So I don't think there is, you know, one type of behavior here, critical behavior, particularly in
I think it's very interesting. I mean, the hope is that here the situation is simpler than the cuprates, but the question is whether there's something like a Kadawaki-Woods or other universal ratios that one can determine near x equals 0.17 and see whether a coefficient enhancement is tied up with the mass enhancement or it is not, right? Yeah. So it seems to me to be very much worth the effort.
Indeed, yeah. I mean, there's something yet to do specific heat at high field, because obviously we'd like to look at the low temperature gamma coefficient. It's something we are trying to develop at this moment, but we're not yet ready to make those types of measurements.
Thank you.
Something we would plan to do, yes.
So one last question before we move on to Amalia's talk from Pavel.
I'd like to ask whether there is any systematics in the dependence of the residual resistivity rho naught on sulfur doping or on pressure. Is there any systematic behavior that one may see?
Yeah, thank you for the question. In terms of as a function of S, it's not, well, clearly iron selenium has an extremely low residual resistivity because it's the stoichiometric material. In fact, this is just well below 1 microohm centimeters. Then typically across this regime, we see values of rho not varying very much, actually. So as a function of sulfur content, of course, you're adding further disorder, but they stay between around, let's say, 5 and 15 microohm centimeters, but no real systematic variation. As a function of pressure, there is certainly a drop, but there you're having to differentiate between the variation due to increase in carrier density, which is clearly happening as a function of pressure, but there is a drop in the residual resistivity as you change the pressure.
Right. Thank you again, Nigel. So Nigel, if you can unshare the screen, and then Amalia, you can share the screen. Amalia.